So here we're going to go over aromatic bromination. An aromatic bromination follows electrophilic aromatic substitution mechanism. And before we jump into the mechanism, we must understand three different scenarios. Starting off with this second one over here. If I was to take an aromatic ring such as benzene and I was going to react it with bromine, I would get no product. There would be no reaction that would occur. You might be wondering why. The answer to this is in the details. Remember, aromatic ring, it's highly stable. Its electrons are delocalized. It's got these conjugated double pi bonds. It does not want to lose its aromaticity. It's thermodynamically stable. So if I was to simply just take the aromatic ring and bromine, they're not going to want to react with each other. But this indicates that this reaction has a high activation energy. What can I do to reduce the activation energy? I can use a catalyst. Because remember, catalysts are used to reduce the activation energy and allow for a reaction to occur due to that reduced activation energy. And that is what we see in this third scenario over here, where we have that same aromatic ring, we have the bromine, but we've added in a catalyst where the iron is going to act as a Lewis acid, and we will see our final product of the aromatic ring and the substitution occur between the hydrogen and the bromine. What's really important to note over here, and it'll make more sense once we go over the mechanism, is that this is going to be our final product, not this. Because remember, this aromatic molecule started off aromatic. We're simply just doing a substitution, so it needs to end off aromatic. This is not a favorable molecule because this is no longer aromatic. It's lost that double pi bond. So this will not be observed as a product. Even if it is, it's going to be very short-lived, and it's eventually going to result into this. The last thing that we need to realize, similar to this scenario down here, is that if we had something that wasn't aromatic and we reacted it with the same bromine, then we would see a final product that has these two bromine substituents attached on. But this is just because we didn't start off aromatic, so it's okay if we end off non-aromatic. But over here, the aromatic ring wants to remain in its aromatic state, so that is why we are going to observe this product. So jumping into the mechanism, what happens? So of course we have our bromine, and bromine is a halogen, and halogens typically, they form one bond. So this bromine is forming a bond with its fellow bromine, and they've got a full octet. But then we have FeBr3, we have iron 3 bromide, which is acting as our catalyst, and specifically the iron is acting as a Lewis acid. So what does a Lewis acid do? Remember, a Lewis acid by definition gains an electron, whereas a Lewis base loses an electron. So here this iron really, really wants to gain an electron. Where can it grab an electron from? Well, it can abstract one of the electrons from this bromine. Okay, so it picked up one of these electrons from bromine, and as a result, bromine has lost one of its electrons and iron has gained an electron. So iron will gain a negative charge and bromine will gain a positive charge, and the resulting two form a bond with one another, where iron has taken one of those electrons from bromine. Now, bromine now has a positive charge, whereas this bromine still has its full octet. It's okay, but this bond now becomes polarized. Why? Because this bromine lost its electron to iron. Now this bromine really wants to get an electron back. Where can it get an electron back from? Well, it could get the electron back from this fellow bromine. But if this bromine loses an electron, it's going to have a positive charge and it's going to want to gain an electron from somebody else. So this is how we've created this super electrophile that's going to react with our aromatic benzene. Remember, the whole purpose of electrophilic aromatic substitution is that we have this molecule that's very, very electrophilic, and that is what's going to cause the aromaticity for an aromatic ring to break. Bromine on its own could not do that, but we have polarized this bond and we've created a super electrophile. How did we do that? Well, iron took one of the electrons from bromine. Bromine has a positive charge. It wants to gain an electron. It's going to want to gain it from right here. But then this bromine is going to have a positive charge. Where is it going to get the electron from? So taking a look over here, so we have our aromatic benzene. So one of those pi bonds is actually going to break aromaticity and it's going to reach out for our bromine. And it's going to abstract that bromine, and as a result, the electron from the bromine is going to go on to this bromine and it's going to get an overall net charge of 0 because it's gained its electron back. As a result, we get this product where, remember, this pi bond broke aromaticity. It reached out for the bromine. Now, you may be thinking, we broke this pi bond, so this carbon or this carbon could have picked up that bromine. And you'd be correct. This bromine could have gone here or it could have gone here. It doesn't really matter in this case, but I've just drawn it out over here. So there's an important thing to understand over here. This carbon, it has 4 bonds, right? 1, 2, 3, 4. Carbon needs 4 bonds, but this carbon has 1, 2, 3, the third being to that hydrogen. So it's missing a bond, so it has that positive charge. Over here, what's going on with our iron 3 bromide and bromine? Well, this bromine, it gained an electron, right? So it now has an overall charge of 0, whereas this iron still has that negative charge. So what's going to happen? First, let's quickly go over this. So once we have that bromine bound, this is called our sigma complex, and our sigma complex will exist in different resonance structures, which we are all very familiar with. So once again, instead of drawing out the resonance structures, you can always draw out the Arrhenius ion, which simply just denotes a dotted line and a positive charge to let us know that the electrons are delocalized. But what happens is now this iron has a negative charge, this bromine has a charge of 0, but this can now act as a base. And what's going to happen is that this bromine can abstract that hydrogen, and as a result, the electrons from that hydrogen will go back down and reform that double bond. Remember, when we're picking up the hydrogen, we're not picking up the electrons of the hydrogen, just the nucleus of the hydrogen. So as a result, these electrons fall back down and we reform that pi bond and we get our final product, which is the aromatic ring with the bromine. Remember, this was a substitution reaction because we initially had a hydrogen over here. We removed the hydrogen. Who took the hydrogen? Well, it was the bromine. And then as a result, that first bromine is now bound. And take a look over here, iron 3 bromide has been regenerated. That's really important to make note of over here because iron 3 bromide, it was a catalyst. It had to be regenerated. So this is essentially the mechanism for our aromatic bromination, where we start off with an aromatic ring and bromine, but we needed that catalyst to create that super electrophile and that polarized bond for the aromatic ring to be able to break aromaticity. And at the end, we had to regenerate our iron 3 bromide, and we get HBr as a product as well. Now, once again, it's really important to note that we do not see this reaction where the last bromine over here, you may be wondering, why doesn't it just go over here? Well, if it did go over here, then we would get the following product, where this molecule is no longer aromatic. And remember, we want to end up being aromatic. So this is not likely. Even if it does happen, it's not gonna be long lasting because this is not favorable. We want to regain aromaticity, and that is aromatic bromination following the EAS mechanism.